Welcome to average rate of change. We are going to calculate the average rate of change given a table of values, and then we'll determine whether the rate of change is a linear or nonlinear pattern. I want to start off by looking at this graph here. We can clearly see that this pattern is linear. This blue line is a straight line, so it's definitely linear. When we're thinking of average rate of change, it's easy to figure out when we have something that's linear. For example, if I want to determine what the average rate of change is for this line, I merely just need to pick 2 points. So say I pick a point up here at 0, 5, and a point right down here at 103. I just need to figure out the change in my vertical distance over the change in my horizontal. This change is what you've often heard referred to as the slope. The slope is the vertical change over the horizontal change. And this works for anything that's linear. So if we were to figure this out, remember that at this point we went left and right 0, but we went up 5. So I'm going to label this point as 0, 5. This point here, we actually traveled 100 miles, and now we're at 3 gallons of gas in the tank. So back here we had 5 gallons, and we burned some. Now we're down to 3. So if we look at the slope and we do our vertical change first, our vertical change is always our y coordinates. So we would say we had 5 gallons in the tank. Now we're down to 3. We started off traveling 0 miles, and by the time we got down to 3, we had traveled 100 miles. You will recognize this, like I said, as the slope formula. If we're to calculate it, we would get 2 over negative 100. And then we could simplify this down to 1 over negative 50. We could leave it like this, and remember what these labels are. The vertical is the gas that remains in the tank, or the gas that is in the tank, and the horizontal is the miles that we've actually traveled. So in one sense, we could describe what we have here. For every 1 gallon, the bike can travel 50 miles. When we're dealing with average rate of change, though, it's better to divide this out. So in my calculator, I took 1 divided by 50, and I got 0.02, which is negative because of the negative sign. The negative just means we're using up gas as we travel mileage. So in other words, we're using 0.02 gallons of gas for every 1 mile that I travel. This is a linear average rate of change. Look at our general definition. An average rate of change function is a process that calculates the amount of change in one item divided by the corresponding amount of change in another. So we looked at the change in the gas in the tank over the miles traveled. So we compared those two. Now let's look at another example. In this example, we're going to be looking at automobile racing, specifically the NASCAR Daytona 500. It's a 500-mile race in which the winner gets $1 million. The average speed and time of the Daytona 500 winner varies from year to year. For this example, go ahead and read through these questions, then pause the video and see if you can actually answer Part A and Part B. For the first question, we need to figure out the difference in race times between 1960 and 1961 in hours. Well, we don't really know any of the race times. We only know that the first guy, Junior, won with an average speed of 125 miles per hour. So we know how fast he went, and we know how far he went. So how did you figure out how long it took him? One thing that you might have used was the distance formula. The distance formula says that our distance we travel is a function of rate times time. So if we are traveling 60 miles per hour and we go for 2 hours, we will have traveled 60 times 2 or 120 miles per hour. Or 120 miles, sorry, not miles per hour. But in this case, we know our distance and we know our rate, but we didn't know our time. In order to figure out time, we need to rewrite this equation. We need to rewrite it as t equals instead of as d equals. Well, how can we do that? We could take d equals r times t, and we can isolate t. So r times t means we have to divide by r in order to eliminate r on our right side, which just leaves us with t here. So time is then equal to our distance divided by our rate. So you may have used this, or you may have thought in your brain, well, if I've gone 500 miles and I'm traveling at 125 miles per hour, if I just divide these out, 500 divided by 125, it'll tell me how long it took me to go 500 miles. It looks like 4 hours. And really what I've done is just use the same formula. I've taken distance divided by my rate to figure out my time. If we do that for the second guy, he traveled a little faster, so I would expect that his time would be quicker. And if I take 500 divided by 150, I get 3 1/3 or 3.33 hours a year later. So as time goes by, the speed at which these two gentlemen finished the Daytona 500 has gone down. If I subtract 4 minus 3.33, I can see that my average rate of change between these 2 years was 0.66 hours. So let's consider this. Between 1960 and 1961, the average rate of change for the following years were 0.66 hours. Well, let's see if that happens between 1997 and 1998. In 1997, Jeff Gordon won with an average speed of 148 miles per hour. So if we divide the distance divided by how fast he was going, we end up with 3.38 hours was his time. Now let's look at Dale. Dale's average speed increased to 173 miles per hour. So how long did it take him? If we divide these, we end up with 2.89. So the key is to determine if the average rate of change between 1960 and 1961 matches the average rate of change between 1997 and 1998. If we subtract these two like we did before, we get 0.49 hours. So we have a different average rate of change. So what does this mean? What is this going to look like? Well, let's go ahead and make a table of values and then graph this. For some of these values, we've already figured them out. But remember, in order to figure out our race time, all we have to do is take our distance, which is 500, and divide it by each of these speeds. When we do that, we know that 500 divided by 50 means that this person would have completed it in 10 hours, this person in 6.67, and so on until I filled out my table of values. So what I've done is I've taken this equation, and I know that my distance remains the same at 500, it's a constant, but my rate or my speed has changed. So I'm looking at the relationship between time and rate. So now what we want to do is we want to graph this to determine if this is a linear or nonlinear pattern. Well, here's my graph, and I need to first figure out what should go on my dependent and independent axes. Well, remember that our race time depends on how fast we go. Well, anytime we can say that, if something depends on something else, then race time up here would be my dependent variable. It depends on speed. So then we would have speed down here. The next step is to define our increments of time. Well, we're dealing with speed here, and our speed goes from 50 to 200. So that means I need to have increments where I can fit anywhere from 0 to 200 down here. For the bottom, for my x-axis or my independent variable, I decided to go by 25s. So I skip every other one and do 25, 50, 75, 100, and so on until I get to 200. Now for my y-axis, I just need to go up to 10. So for this one, I'll probably just count by ones. Now I'm prepared to plot my points. My first point is here at 50, 10. So I would go over here on to 50 for speed And then I would go all the way up to 10 right here and plot that point. Let's go ahead and plot the rest. Now that I've plotted all my points, I can clearly see that race time does not change at a constant rate. If I connect these, I end up with a curve. I can still make predictions. However, this is a non-linear pattern of change. There's still a cause and effect relationship between one independent and one dependent variable. However, this is truly a non-linear change, and you noticed it when we went back here and we calculated our average rate of change. If this had been linear, then our average rate of change between any 2 years would have been the same. But we can clearly see by the graph that our average rate of change will be different between any of these 2 points. You should note then that equal changes in speed do not produce equal changes in race time. That concludes our average rate of change lesson today. You should be able to calculate the average rate of change given a table of values and determine whether the rate of change is a linear or nonlinear pattern. You should also know and understand the relationship between the 2 variables that you are given. In this case, as speed increases, our race time decreases.